So welcome everybody to this first session of the year of the Chilean Probability Seminar. We have the pleasure to have with us Kosuke Yamato, yes, from Kyoto University, that will speak to us about existence of quasi-stationary distributions for downward skip-free Markov chain.
Yes, thank you for introduction. At first, I am so grateful for to having an opportunity to talk here. Thank you very much. So, as the title says, I talk about existence of quasi-station distributions for classical Markov chains which have downward skip-free property. I'm Kosuke Yamato and from Kyoto University in Japan. So, I start from the definition of quasi-stationary distribution. Okay, thank you. So, first I give a general definition. So, let X be a Markov process on some state space S, and let zeta be its lifetime. So, we consider a Markov process with killing. Then, a probability measure nu on S is called quasi-stationary distribution or QSD when this equality holds. So for every t, for every positive t, so the log of x of time t starting from nu is equal to nu. So this shows a kind of stationary phenomenon. Since the first initial distribution condition to survive at time t is invariant in time. So this is why we call quasi-station distribution. When we forget or ignore this conditioning part, so theta is larger than t, this definition is exactly the same as the stationary distribution. So the quasi-stationary QSD is a concept analogous to the stationary distribution when the process has killing. Okay. So it is in some sense quite similar to stationary distributions, but it is it has many differences. So one big difference is important in this talk, and so it is that so there may be infinitely many QSDs for irreducible Markov chains. So it is a very well-known result that for irreducible Markov chains, so conservative irreducible Markov chains, there are at the most one stationary distribution. But QSD may exist infinitely many, maybe infinitely many. So this is a big difference. So I first give some example, so which shows which has infinitely many QSDs. This is a result by Cavender's 78 result. So let X be a Barsand-based process on natural numbers, and we consider it is killed at 0, and whose Q matrix is given by this form. So the left transition is given by a transition rate is given by mu, and the right transition rate is given by lambda. And we are supposed so lambda is less than mu. Then this this Markov chain X has infinitely many QSDs parameterized by QSDs nu gamma and parameterized by some interval between 0 and gamma star, where we define gamma star lambda plus mu minus 2 square root lambda. So here, so detail is not so I'm sorry. So the QSD nu gamma is given by this form. So here the detailed form is not important here, but the importance here is there are infinitely many QSDs. And when we forget killing at 0 and give a somewhat reflecting boundary condition at 0, we have a conservative Markov chain, which is actually a somewhat simple random walk, simple asymmetrical random walk reflecting at 0. And it is, we can easily see that it has a unique stationary distribution, which is given by this pi, which mass after x is u over lambda powered by x times by some normalized constant c. So, as you can see, so QSD and station distribution and QSD are totally different. And so we can see that there is a big difference between QSD and station distribution. So the topic of this talk is to consider the existence of QSDs for downward skip Markov chain. I explain the definition. So let X be a continuous time Markov chain on negative integers, and I denote that by how X the persisting time of X. Then X is I say X is downward free when for non-negative integers X, Y, Z aligned in this model. When we start from Z, Y must be hit before X. So this is the downward definition of downward skip. Or we can say, in other words, this definition. So it's maybe more simpler. So it is the size of downward jump of X is always 1. So I like so this is non-negative integers. That's a set of non-negative integers, and the jump from X to, for example, is can be 2. Can be so on upward. What size of jump? The size of jump is not restricted, but the downward jump is always 1. This is possible, but this is impossible. So this is definition of downward. I think it is not so difficult. And the example of the processes satisfying this downward skip free property is, for example, Bass and Best processes, via name Gordon Watson process, which is sometimes called simply a branching process. So these are the examples of downward skip process. So now I go on to state main results, but it needs some a little long preparation. So I first state very simple form in a very rough form in just main result of my talk. So it is the following. So let X be a downward skip free Markov chain such that the lifetime zeta is given by tau 0, the persisting time at 0. Then the main results are twofold. One is to give a necessary and sufficient condition for existence of a QSD. And the other one is characterization of the set of QSD. So as I have already explained, so there may be infinitely many QSDs. So the characterization means, so what is the set of QSD? It can be empty or singleton or more general. So I will give how the set of QSD is given. Yes, so I explain my motivation of this step. And to see this, I explain some known results for existence of QSDs. There are some general criterion which we can apply to many kind of processes. So there are 3. Here I introduce these 3 studies by Kingman, Ferrari, Keston, Martinez, Pico, and Takeda. And so one is the Kingman's one, and it is called R theory. I don't explain the details here, but it gives us general criterion for the existence, a unique existence of what QSD corresponding to the decay parameter. And the second one is I give a criterion for existence of, so there exists existence of at least one QSD. For Markov chain satisfy this condition, which says so. This condition is a little abstract, but roughly speaking, so this condition states the state space is large. And the third one is the academic research result, and it gives a criterion for the unique existence of a QST for symmetric manifold with the tightness property. Here I don't explain what is the tightness property, but I just mentioned remark that so this tightness property is a totally different concept from the tightness of probability measures. So there are these general results. These results are very useful because it gives it ensures the existence of QST, but it not these results does not necessarily give what how many there how many QSTs exist or what is the form of QSTs. So to give such detailed information, we need some detailed analysis, and it was done by 4 specific processes. And I pick up some examples of class of processes which we have already known the detailed. So one is the finite manifold thing. So this is very simple, and we can see there is a unique, or there are always a unique QSD by from Perron-Frobenius theorem. This is very easy, and I don't know who first mentioned this one, but the second class of processes is Barsan-Dess processes. So Barsan-Dess processes was very QSD. QSDs for Barsan-Dess processes have studied by very many authors, but I think so. The characterization of QSD, the set of QSDs, so it was established by Van Doorn in 1991. And there is also, and so Yanemi-Gorton-Watson processes was first studied by Yagro in 1947, very pioneering work. And recently, so Maillard gave us complete characterization of QSDs. So one-dimensional diffusion was the QSDs for one-dimensional diffusion was also a very classical topic, and there are so many studies, and I don't pick up any specific studies. So, but one-dimensional diffusion, so QSDs for one-dimensional diffusion are completely known now. And so, and the last example is the spectrally positive Levy processes, which is a one-dimensional Levy processes without negative terms. And so which has whose Levy measure is supported on the positive. So this was so studied by Bertrand's very well-known work on the finite interval case, and recently I studied the half-line case. And so this was just accepted last week. And so for spectral Levy processing was completely known. So QSDs for spectral positive Levy processes are completely known now. But I think these examples are so somewhat so not so many, and there are, I think there are many more general classes of processes we can characterize QSDs completely. So the motivation with my study is to give more general examples. Yes, this is a motivation of my study. So this is so now I finished the introduction, and now I explain so the approach of my study, and then I give some preliminary results, then state main results. And I think I don't have enough time to explain the proof. So I just mentioned some outline or important property for the proof. So now I explain the approach. So my approach can be stated in a phrase, so which is a generalized state function plus its analytic extension. So of course, this does not make sense for many people. So now I explain in detail. So my main tool is the generalized scale function. So which is the generalized one for the scale function, and scale function is the object which was quite widely used in the study of spectrally positive Levy processes. So I give the definition of it. So let Y be a spectrally positive Levy process, and let C be its Laplace exponent. So that is, C is the logarithm of Laplace exponent, Laplace transform of Y1. So C beta is always finite for positive beta because of the spectral positivity. Then Q scale function is defined as function satisfying this condition. So before the stating the definition, I mentioned that this kind of so good difference for scale function is the Cipriano's and the textbook on Levy processes and Bertrand's textbook on Levy processes. This is very good introduction for scale functions. These are very good introduction. So Q scale function has a parameter Q, and so the function WQX is defined as the unique function on satisfying continuous increasing on positive half line, and which is 0 on the negative half line. And its Laplace transform satisfies this equality. So 1 over the beta minus Q for So of course, this definition is very implicit, and so I don't know what is the scale function, but the explicit definition is not important here. And the important point is it satisfies it is very useful to give some formulas. And what is the exit time formula? So let me ask myself interval 0, A, and take up x as the internal point. Then the Laplace transform of tau 0 condition on the set tau 0 is less than tau A plus. Tau A plus means that is the fastest time greater than A. So this exit time is just represented by the ratio of scale function. This one, WQA minus X over WQA. And potential density formula is also given by scale function. So the Q potential of Y on the Y killed on exiting the interval is given by this form. So very simple formula, and it can in some sense from this formula we can say that every information on the interval can be extracted from scale functions. Scale function very useful object. So the Bertrand uses this scale function to the study of QSDs. So this is
just as one question, so to try to understand this scale function, what is for the Brownian motion, for example?
Brownian motion, when the Brownian motion width is given by some sine hyperbolic function, I think I'm not sure, sine hyperbolic function, or yes. Yes, so I still have prepared for that. So I think so.
It doesn't matter. I thought it was a simple form.
Okay. So it does not necessarily simple, but so it's an exponential function. I think it is a sine hyperbolic function. I think. Okay.
Thank you.
Bertrand studied the existence of QSD for spectrally positive Levy process on the finite interval. So it means he considers the QSD for zeta. Lifetime is given by the exit time of the finite interval. And his method was to give an analytic extension of scale functions. So he showed that for fixed x, the function q2wqx is extended to the entire function. And this is very easy but important property. And then he applied R theory for general. So for this kind of thing, it is very abstract, and I explain how these properties are applied in the next slide. But I first state his results. So he showed that there exists a unique QST nu. And then nu is represented by the scale function extend to minus log. And so nu is this form, and this log is defined by the first minimum root of the scale function in some sense, and that law is gives the key parameter of the QST group. So this is his result. So now I explain how he derived this formula, this result, very lastly. So the content of my talk is not necessarily the Levy processes. So this is in some sense not related to my work, but I think, but I don't have enough time to give the proof. So introducing his proof will give some insights how scale function is applied. So this is the Bertrand's argument. So at first, so by showing that WQ is extended to entire function, this potential density formula is extended to the right hand side is extended to the complex plane. Then from some simple observation, we see that this right hand side has a pole, simple pole at low. Sorry, minus low. Then, since this right hand side is meromorphic function, so the pole is has some finite. The degree of the pole is always a finite order. So we can take some n such that so this divergence holds. Then this formula shows the Laplace transform diverged as q to some negative number in a polynomial order. So for this kind of asymptotic behavior, we can apply a Taubarian theorem. So which is in this case, so we can apply the Karamata's Taubarian theorem, which is very famous elementary result, and then we have this asymptotic behavior. So now we can use R theory for general Markov processes. It shows that from the theory, from the consequence of the theory, we see that this quantity, exponential roti times like this probability, has limit at t to infinity. Combining 4 and 5, so we see n must be 1, and the limit is and we call this form. The limit is computed by this form. Then so once we know this limit, it is easy to see that so this w minus rho y dy gives a quasi-extensive distribution. But by normalizing by some constant. Now this is the Bertrand's argument, and this shows that why scale function is useful and why analytic extension is very important in this argument. So this is the why scale function is useful for study of quasi-extensive distributions. So, but this is just for the theory for Levy processes. So, there are by generalizing the scale function, we can apply the scale function for more general classical processes. So that was established by Nova in 2020. He introduced a general scale function for standard multiple processes on interval without negative terms. So he showed that the scale functions are defined, can be interpreted as some excursion measure. So his definition of scale function is very simple. So let the q be positive number and y be some point, and let ny be excursion measure away from a point. So it is a schema finite measure on a path space on the path space, and which has mass on path from y, starting from y to starting from y and killed at the first return y. It is excursion measure. Then his definition of the scale function is this form. So wqxy is given by an indicator of 1. X is less than 1 over Laplace transform tau x under excursion agent in y. Then he showed for these scale functions, so similar formula for x time and potential density formula holds. So it is quite similar to the one for Levy processes, and where so Bn is a reference measure, and I don't explain here in detail, but for in some mild setting, we can define general scale function in more general setting. So for when x is scale positively processes, so wqxy is given by wq0y by space homogeneity, and this was the this is why this is that can be said to the generalization of the scale. Yes. So then my strategy is the following. So introduce Q scale functions, generalize Q scale functions for skip-free downward skip chains, and then extend it to the analytically extend the scale function to entire function. So Nova's results just Nova's definition is just for non-negative Q, so we need to extend the entire function. And then once we have extension, we can use a similar method for the spectral Levy process case. So, but this kind of similarities does not so this kind of strategy does not work so easily, but especially there are two big differences. So one is that this analytic extension is not established, and so since now we don't have space homogeneity, we need to care about the behavior around the infinity. So this is two big differences, but this difference can be overcome and so it holds up. So the extension is always possible, and the behavior around the infinity can be controlled by classification of the boundary, which is a generalization of Fermat's classification of the boundary, which is famous for Boas-Samples processes. Yes. So, I don't have enough time, but I explain preliminary. So, so let X be the number of primal constraint on N, and let I denote its Q matrix by Q. And I assume X is irreducible and regular on positive integers. So it means non-zero X and every Y. So the fit from X to Y is possible. And the regular means so for every point has a origin time. This is not so special assumption. It is very usual, I think. Then I define local time at X by just the occupation time of X at the process X at state X. And I define the excursion measure Nx of X by the Qx times by the path starting from X and killed at X. So theta is the shift operator, and this has a by shifting tau n at minus X, so we set X that immediately exit to the point X, and then by this part, so I kill the path return of X. So this is very simple definition of the excursion measure. And so when as excursion measure is given, so we can define inverse local time, and then its inverse we can define local time. So, but here I define local time and excursion measure separately. But this normalization excursion measure is that, so the definition is so these two definitions is so somewhat consistent, which means the inverse local time, which is the right inverse of LTX, is given by this form. This is to say a small point, but I just remarked. Yes, now I define the scale function or generalize the scale function by this form, which is exactly the same by almost the same by Nova's definition, and and by exactly the same argument by Nova, we can show this exit problem, and this formula holds. So this is not essentially not a new result, just application of Nova result. Yes, and now I have scale function. Now I can specify.
So just one question there.
Okay.
Why? So where in a way you are using that it is skip free?
Yeah. So I don't explain the so the skip free property is important to derive these two formulas. Yeah. So now I state main result. First one is the to give analytic extension of the scale function. So which is somewhat abstract result, but it is very important. So for the definition of terminology, I say that the M is so natural integer. So infinite matrix M. I say that it is M is triangular when its lower triangular element are 0. So we should, in that case, we say that M is triangular, and let I be some identity matrix. Then, so for positive Q, the following holds. So the matrix, so we see that WQ is a matrix. We can see WQ is a matrix, and so then in that case, the matrix F equal WQ is a unique triangular matrix solution of the equation. So QF equal I plus QF. But so this so this is of this form. And this is not the second one is most important. So from the assertion one, we can show that WQ has this somewhat Neumann series expansion, and we also see that so for fixed X and Y, from the triangular property, this infinite sum is always finite sum, and we have this expression. And since this expression is polynomial, so we can extend analytically extend WQ by this equality. So this gives analytic extension of scale function. Then, so from third assertion is almost immediate from 2. So it shows so WQ for every complex number Q, I minus 2W is invertible, and WQ is I minus 2W inverse times W, or W times I minus 2W inverse. So WQ is, so in this sense, WQ is somewhat W is both of the scale function. WQ is all WQ is represented by W. Yes. This result shows, so summarizing, this result shows WQ is a polynomial and can be extended to analytic function. This is the main one.
Let me change this.
Okay. From this formula, we can see resolvent identity. So this formula, which is a somewhat easy consequence of the third assertion. Yeah. And substituting R equal 0 in this identity, which is that F equal WQ is the solution of this equation. This is a discrete volatile type integral equation. And since the scale function for Lie processes or some one-dimensional diffusion are defined by integral equation, so this shows that the definition of scale function is natural in some sense. Yes, this is the first result. The second result is existence of QSD. So let lambda 0 be the decay parameter, which is the maximal value of the tau 0 is exponential integral. Then, so this parameter is very important because if nu is a QSD, tau 0 is exponentially distributed under nu. Then that positivity of lambda 0 is a necessary condition for existence of it. Yes. I introduce a classification of the boundary. So I say that the boundary infinity is entrance when the sum of W0x is finite. And when the sum is infinite, I say that it is no entrance. So this classification is somewhat so strange, but it is a very natural one in some sense because when X is a Barsan-Dess processes, we see that W0x is Sx phi x, where Sx is scale function for Barsan-Dess processes. It is very classically known. So this is not different from our scale function, but and the pi is a speed measure, measure speed forward measure, which is a very well-known object in the theory of Barsan-Dess processes. Then W0 since W0x is Sx and pi x. So the boundary is entrance is equivalent to the sum of Sx pi x is finite. So this condition is in fact the same as the definition of entrance condition by Ferrer in the theory of Barsan-Dess processes. So this definition is a very natural one, and it seems somewhat not naive generalization, but it actually works. And so I give some examples of boundary classifications. So, but I don't have enough time. I cut here. So I state my main results. So I assume so X certainly fits 0. So it means that tau 0 is finite with probability 1. This is not strong assumption. So this is my main result, theorem 3. So let Q be the set of QSDs. Then the following goes. So when the boundary infinity is entrance, then it always holds lambda 0 is positive and QSD is singleton, new lambda 0. And when the boundary is no entrance, so we need to assume lambda 0 be positive. To be positive. So then Q is given by new lambda, and the lambda is between 0 and lambda 0. So in this case, there are infinitely many QSDs. Here, the measure new lambda is given by this form, so which is lambda W minus lambda 0x, which is given by scale function extends to negative parameter. This is similar, a very similar result to Beltran result. Yes, so this gives the characterization of QSD. So I give a remark. So Kijima gives a similar result for. So Kijima in 1993 paper studies so existence of QSDs for downward stream Markov chains, and he gives some partial results. But this result gives some extension generalization of his result. So this is the main. So once this is established, so we can some. So once we know the existence of QSD, the next point is it is somewhat so the QSD can be a Yagrom, which is somewhat limit to distribution of conditional probability. And in the entrance case, I can show that the unique QSD is Yagrom. This is so some easy application of R theory. So we have this result. So when the boundary is entrance, the unique QSD new lambda 0 is a Yagrom, which means from every starting point, condition the probability at time t is converged to new lambda 0 y as t. And here we can allow the starting point of takes, but the state infinity. But I don't explain how we extend the state space to infinity. I can extend it in a natural way, and this diagram holds for starting point of infinity. The last result is the characterization of the parameter lambda 0. So it is lambda 0 is characterized by this form. So the non-negativity, so the slope of lambda, which satisfies w minus lambda 0x, is w minus lambda 0x is a positive function as a function of x. So this kind of characterization for lambda 0 was given by Mandu for one-dimensional diffusion, and this this kind of characterization is sometimes used, sometimes useful. Yes, this is the main. And I think so. I give some small remarks on the proof, so I don't have time. So theorem 1 shows that the scale function is analytically extended to the entire function. The proof is essentially so elementary. So it is very typical result. So the lifetime Laplace transform of the lifetime is eigenfunction. Is a very typical. Sorry. So it is very typically holds that so the Laplace transform of the lifetime is eigenfunction of the generator. And the idea of the proof of theorem 1 is somewhat similar. But we need to do some the idea combining the idea with the diversity property, but it is not so difficult. I don't explain in more detail. Yes. And theorem 3 is proved by a combination of small observations using the potential density formula and result identity. And so it is difficult to state. So what is the important point is, I don't say in a word, but why scale function is useful. To show why scale function is useful, I just give us a simple give us proof of a simple lemma. So which is which says that so if nu is a QSD such that the key parameter is lambda, then nu must be of this form. So this lemma shows so that QSD must be represented by scale function. The proof is very easy. So on the one hand, by the potential density formula, we have this equality. So actually, I have. Sorry, I just slide. So potential density formula was given by for some finite interval, but by taking the limit z to infinity, we have some half-line case, and we have this equality. On the other hand, since nu is a QSD, we can by importing this and changing this to conditioning and some computation, we have this equality. Then these two left-hand side is equal, so we have this equality, and then by matrix notation, this equality is nu I plus lambda w equal lambda w, and by taking the inverse, we have new must be this form. So this is why QSD must be this over this form. So here the potential density formula for the central part. So yes, but I don't have enough time to state more detailed results, so I just mentioned this proof of this lemma. Yes, this is a summary of my talk. First main result was the general function. I introduced the scale function for the multiple chain and extending it to the entire function. Then applying the result, I can show characterization of QSD by using boundary classification. And so in the entrance boundary case, I can show QSD is like actually average. Yes, this is all. Thank you for your attention.
Thank you very much. So are there any questions?
Well, you use intensively potential theory because some of the concepts you are using are.
Sorry?
You're using intensively potential
Yes,
theory.
yes, I the problem by potential theory.
Yeah. It can be, so in principle, it can be extended to more general spaces. But in Kyoto, potential theory.
But why this kind of potential theory was not so popular. I think so British form is very popular. But I don't know about it.
Because there is a whole school and
the skip free part is to control, I guess, to control some of the extensions and so on. But can you do it if you have the left jumps are bounded?
Boundary case.
Because that was studied by Cerveda and Keston. In the other direction, I don't remember. The jumps upward.
Yeah. I think it's difficult. I think because the scale function theory is deeply depend on the downward slippery property because actually the proof of this formula is quite simple. So I will give this formula. So the point here is to LZ cost. So this formula is derived by just by application of this multiple property. So since now you must X, Y, Z is aligned in this order. So starting from Z, before hitting when we start from Z, before hitting X, we must hit Y. So this formula, and so by the Markov property of X measure, we have this and our X and our. So by dividing this, we have the very simple proof. And so in this proof, for downward slippery property is essentially used. And if we skip, if only a single point, this time exclude a lot of work. So I think so. Free property is essential in this work.
Yeah, something like that happens in diffusion theory.
Yes.
Because if you want to pass from X and Z to X, you have to pass through Y and so on.
Yes.
Yeah, right.
Any more questions? With the no more questions, I propose that we can again.
Thank you very much.
So we have some time before the next block, so we invite you to take some cookies and some juice. plus 40 plus 5. Let us see equal to the plus 5 maybe it goes. Because the usual plus 5 is end of the
We need to copy some formula that
But you can pick this once.
Yeah,
Huh? So you send the step, but also your archives.
It's just this formula.